Thank you. I'm Koji from Kyoto. So I'd like to thank the organizers for finding the invitation to present my talk here in the exciting workshop. So my talk is dedicated to how to formulate quantum gravity using machine learning. So I just try to propose one way to use machine learning to explore the definition of quantum gravity. So what is quantum gravity? So gravity actually treats geometry, like smooth geometry of this universe. And then if I want to do quantum, that means that you need to sum over many geometries with some weights defined by Einstein action. And if you want to do that numerically, then of course you have infinite number of geometries. So you need to make it finite using numerical techniques. So to do that, of course, you need to parameterize this smooth geometry by finite number of parameters. So how can we do that? Of course, in history, we know that dynamical triangulation for two-dimensional Euclidean gravity works. And there, you approximate smooth geometry by using triangular lattice. And then you have a finite number of parameter space images. So you can do some numerical computation of quantum gravity passively, right? And that worked for two-dimensional Euclidean gravity. However, there was the difficulty found in going over to 3 dimensions or 4 dimensions, or even going to Lorentzian geometry, in which we live. So my proposal is to use machine learning to make a different way of discretization of smooth space-time. And this is actually accelerated by machine learning, as I'll explain in this talk. So unfortunately, I cannot report about my quantum part. That is work in progress. So today, I just like to report my result on classical discretization of classical geometry. So this work has been done in collaboration with Naito-san. Great. So Naito-san in Riken and Naito-san in Nagoya. So they are son and father. So Naito is father, he's a mathematician, and his son Naito is a hardware physicist. We are working together on this quantum gravity topic. And one paper was accepted in ICML 2023 workshop paper. ICML is International Conference for Machine Learning. And another paper was accepted as well. So let me start. So first, I'd like to mention 2 important machine learning papers. Some of you might already know it. So this is one paper by Hanin and Roy. So on your left-hand side, this is how machine learning can recognize the 2-dimensional space as a partition. So on your right, you have a neural network. The input is just 2-dimensional. And the output is, the output would be just 1-dimensional. The input 2-dimension is just x on y, and this figure. And this xy 2-dimensional space is partitioned into discrete patches, right? And neural network can do a classification, as was reviewed in this morning beautifully. And here is one example of partitioning this 2-dimensional space. And remember, for example, in geological map, you have a partitioning of 2-dimensional space as a kind of height function. If you look at the geological map, then there is a equal height lines, and because of that, this height function is classified onto patches, right? So here, not like this equal type function, but it's a triangular shape of two dimensions. So in this way, geometry, the smooth geological height function, can be approximated by neural network by application of this universal approximation theorem in this way. So this is one illustration of how machine learning can represent very complicated space. And another paper which I want to introduce to you is this renowned paper by Google. So what Google did in 2011 was by using a kind of a neural network which is called autoencoder. They tried to classify many images. And don't worry about this complicated neural network, but the result of this training of many images by using a huge neural network is that after the training, if you look at one neuron, and if you try to excite this neuron and not others, then you have a very special image. And that was so on your right. So here is the human face neuron, which was discovered as an automatic generation of a single neuron. So this says that machine learning neural network can recognize many features hidden in images, and so some of the neurons are quite important to recognize patterns. So this one is speech. So this one is shaping. So okay, so these two important papers are found in neural network, and I'd like to apply that to quantum gravity. So there are two strategies. So I introduced two papers, and I can use those neural network technologies to consider or apply to quantum gravity. The first one is generative models for space-time and metric. So you prepare a neural network and consider an input as X. And then the output is a function, right? And this function could be any function, which depending on your program. And in our case, since I want to generate geometries, so the output needs to be this metric. But to do a quantum gravity, as I said, you need to have only a finite number of parameters to parameterize this G mu nu. And in fact, if you generate G mu nu in this way, then the number of parameters in this neural network is finite. So this is the best way to generate geometry for quantum gravity. So the output needs to be this partition space-time. So what is the other approach? So this is what I call ADS deep learning correspondence. So in this case, you prepare some neural network and consider this neural network as a space-time. So this itself, so this interpretation is different from the first one. So if you prepare a rectangular shape neural network and regard this depth direction as R direction, and this vertical direction as space direction S, then so this vertical direction could be understood as a time. It's a space-time. And you train it with some boundary conditions. And then after the training, you have a limited weight distribution on this space-time neural network. And if you can interpret the distribution of the weights as a geometry, then all of the weights correspond to the metrics and so on. So these two are quite different. In particular, the latter one is a new interpretation of neural network. And in fact, this interpretation looks quite like an ADS-CFT correspondence. So why is it? suppose you train with some specific set of images using this neural network, and then found that important neurons are distributed in this way, okay, as Google did. And then you distill this neural network by throwing away all unnecessary neurons. And you have found that the remaining neural network is a sparse neural network. And then if you count one neuron in one space in this neural network, then you have this kind of function, which is very, which looks quite nicely with the similarity with tensor network, which we use in ADS-CFT correspondence. So this kind of idea has been tested in many input-output images. I mean images as a data of CFT. Then CFT data is in here, and then you train everything, and then geometry emerges. So this is really like ADS-CFT correspondence with CFT. And to reproduce the CFT correction function, you need to prepare ADS space. ADS is emerging. Yeah, please.
Tensor network story, you have a number of blocks decreasing as you go down some patches. RG or
here, yes, indeed, you can see the number of neurons decreasing after the training. It's automatic. Yeah, it's automatic. So CFT is prepared here. And then if you want to implement ADS in the other side of the tool, we use the parts. And then using this input output relation, and then you can look at the geometry. Then you can actually make sure that I guess a lot of clouds net is nicely built.
That is architecture dependent. So dependent upon the configuration for architecture. So in the sense that you have much richer structure than just what you have test. And also things like that the interpretation of polymetric years. It's an non-trivial thing if you think about things, skip correction.
Sure. Yeah. Thank you for the comment. In fact, to have a nice interpretation of this thing as an ADS, of course, there should be some ball field which is propagated from this field. And to map this scalability equation, for example, on this surface space time to neural network, we need to prepare a very special neural network. And only in this very special neural network, you have a space-time interpretation of neural network weights. Thank you for the comments. So today, so in fact, there are many work on this ADS deep learning correspondence, but I don't talk about that today. And today, I'd like to talk about this first case, the generative models for space-time and metric. And let me tell you a little bit about some related work. For example, in recent paper by Halverson and Rue, they proposed how to generate this Calabi-Yau metric using this kind of technology. And they call it the metric neural tandem kernel. And this is an interesting technology. When the number of neurons for each layer becomes infinite, then this neural network has a very nice property, which is analyzed by neural tangent kernel. And using this, you can generate a classical geometry. And so my point is that rather than that, I'd like to try quantum gravity by making a path integral over these weights. And in fact, if you do path integral over weights, then there are interesting in development these days, mostly by this initial paper by Halverson, Mikey, and Stoner, which is called the neural network quantum field theory correspondence. So if you make passing of weights, then you have generated fields which looks like quantum field fluctuations. And this idea was based on very old analysis with random hypothesis. And also, I'd like to make a comment on recent papers on feature learning of lattice polytopes. So I'm going to talk about polytopes in this talk. But if you're given a certain polytope, then how can we get the topological property of that? That can be also questions that are studied by machine learning, and these people are working on that. So maybe in this workshop, Eddie Hayes will talk about that on Friday. So let me start my story. So I divided my talk into 5 parts. Maybe I don't need to make a review since there was a good review this morning, but very briefly, I will give you a neural network review. And then I'd like to make a review on neural network quantum states. So how quantum states can be approximated by a neural network. And then I'd like to tell you a very simple toy model of solving quantum mechanical model with neural network. And then interpretation of this obtained quantum mechanical wave function approximated by neural network actually leads you to generative discrete geometry model by using neural network. And finally, I use this to generate many kinds of polytopes by neural network. And this is a classical discrete geometry by neural network, and this could be used for quantum gravity. Okay, so let me start with my review. So here are many neural networks, and for those who don't know what the neural network is, you can just remember that for each figure like this, there are circles and lines. This corresponds to functional ansatz. So this function is parameterized by weights, which are by these lines, and just that. And there is an universal approximation theorem. If you have a complicated, so if you have a large neural network complicated enough, then it can approximate any function. Okay? And in this review, what I need to emphasize is that, for example, so for activation function, we can use this very popular activation function, which is ReLU. Which looks like this. So it's a kinky function, this. And there is a smooth version of this ReLU, which looks like this. This is called soft plus. So in the following sections, I mainly use this one, but I try to replace this by this to have an interpretation of what the neural network function is. Okay, so let me go to the review of neural network quantum states. So there have been quite a big progress on how to approximate quantum mechanical systems by using neural networks. And most of them are for spin systems, so the discretized systems. And in section 3, I'd like to go to a continuous system like harmonic oscillator. That could suffice better our purpose. So, but before going to that, I'd like to give a review on spin systems. So what's the neural network quantum states? So quantum mechanical problem of undergraduate course is quite easy. So once you are given Hamiltonian, then what is the ground state and the excited state? What the energy eigenvalue? So if you like to bring this to a kind of minimization program of energy for finding a ground state wave function, then that looks like this. So this is a given Hamiltonian in spin system. And then you prepare some ansatz wave function and compute this energy expectation value. Right? And suppose that this function, wave function, has some parameters. Then you tune the parameters to make this energy lower and lower. And if it reaches the minimum numerically, then it's a candidate for the ground state wave function. So that's easy, right? And in machine learning, of course, you can replace this energy function by loss function. The loss is lowered by machine learning algorithm, then you get some final answer that is a ground state wave function. So before the era of machine learning, what people use is an ansatz made by hand. So for example, the popular ones are matrix product states and tensor network states. So what are matrix product states? So suppose you have 4 spins like this, and for each spin, you associate this triangular part, which is called tensors. And in this matrix product state, this is a matrix. A matrix depending on this spin. So whether you have up spin or down spin, you have 2 kinds of matrices. And then these horizontal bars means that you have a product of these matrices and take a trace. Okay, if it's the spins are aligned on the ring, then you need to take a trace. So this is the ansatz wave function. So this wave function depends on each spin as is expected, and then parameters are the entries of these matrices. You can choose the size of the matrix as you like, and it's called the bond limit. So this is one good ansatz, and you can reduce the number of parameters from exponential to polynomial. So this is good for numerical purposes. However, this wave function should be good only for locally interacting Hamiltonians. If you want to go to critical systems, then the interaction is long range. So there is no hope to use this ansatz to reproduce the ground state wave function. So people invented better wave function ansatz, which also works for critical systems, and that is a tensor network states. So instead of plugging all A's on the horizontal axis, you prepare another matrix B, which contracts 2 A's like this. And you have a building mountain-like structure using this. Then you can easily access from S4 to S1 like this. So this can represent long-range interactions. But in this way, people try very hard to prepare for some ansatz to look for ground state wave functions. And what machine learning actually enabled us is not to use these kind of very special ansatz, but just use a general neural networks. So for example, let's look at the bottom picture. Here, the wave function, S1, S7, and consider the wave function as an output of the neural network. It is just a one layer. It's a single function. And these are weights, bias, this input of the application function, and it's one neural network, which is represented by this neural network architecture. And this is quite simple, right? You don't need to worry about what kind of architecture is necessary for this. If this is complicated and wide and deep enough, then this can approximate any wave function. And you can train. And in fact, there was a quite a groundbreaking paper by Kari and Troya in 2017. They discussed a 2-dimensional anti-ferro Heisenberg model using this kind of ansatz. So they used not the feed-forward neural network, but they used restricted Boltzmann machine. But they succeeded in breaking the record of previous ansatz like this. So the horizontal axis is a number of hidden units, where you have increased number of units in the hidden layer of this neural network, and the vertical axis is the energy of this neural network states, and it goes lower than these dashed lines. These dashed lines represent the earlier energy values, which was attained by tensor network states. So this was a huge success. Since there was tensor net, we should find to minimize the energy. So rather than that, we can just use the ordinary neural network to find ground state wave functions. So why this is possible? There are many works which try to relate tensor network states and quantum neural network states. And it's interesting since, as you see, neural networks are tensor networks, and tensor networks are neural networks. So they are kind of including both. If the structure is large enough, then it can accommodate the other. And also, feed-forward neural network can be embedded into tensor network states. And there is a mixture of those which have better ability. So in this way, for the spin systems, Hamiltonian eigenvalues are lowered quite nicely by neural network, and this was a huge success. So far we have a spin system, but we are interested in continuous system, right? Since we have X space as an input, and that is a continuous space rather than spin system. So we are interested in what kind of discretization effect actually neural network produces. And also, if I want to do gravity, then topology of the base space is important. And furthermore, what kind of representation space neural network has, that is important, since I want to represent many many spaces with different topologies. So let's look at these kind of questions in later sections. So in the next section, I'd like to talk about a continuous system solved by neural network. So we prepare harmonic oscillator like quantum mechanical system and find a ground state wave function. Okay. So what is the question for this section? For a given Hamiltonian, like harmonic oscillator, I'd like to solve for a ground maybe excited states. It could be one-dimensional quantum system or multi-dimensional, or one particle or many particle, also no phenomenon, as you like. Maybe this can be used for nuclear systems. So what is the strategy? As I mentioned, this strategy is quite simple. First, you prepare your quantum mechanical Hamiltonian on a lattice. On a lattice means that you have X space and you discretize it and consider the value of X as an input to the neural network. Of course, you can choose many points in space. Okay, the neural network input is a spatial coordinate values X, which could be on a lattice. Okay, and then neural network output is the wave function value F. Right? So what is the loss function? Loss function is the energy expectation value for the whole lattice. So this is quite simple. And finally, I train neural network and obtain the ground state wave function. Okay, so let me show you the simple case. So the Hamiltonian for quantum mechanical system could look like this. So you have a Laplacian, you have a potential, and you have an interaction among particles. Then what kind of neural network which I have? So for example, in the one-dimensional one-particle case, the input is just X. The output is wave function psi of X. So you have one unit input, one unit output, and in between you may have a very complicated neural network. An activation function use this sort. Let me show you the result. So for example, one particle case with this potential, that is a harmonic oscillator, the result looks like this. So here the value of omega, which is chosen to be 1.0 for this omega. And then this is a neural network architecture. So I have two layers in between. The first layer consists of 4 units of neurons. The second layer 4 units of neurons. So we have different architectures like this. The result looks here. So in total, you have energy 0.5. That is what we expect, right? So for omega equal to 1.0, then energy need to do 1/2. So this is perfectly good. And if you look at the neural network wave function, then it looks like this. So it's completely nice Gaussian. I'm sorry, So this red line is the exact Gaussian function, and the neural network trained wave function are these colored lines, but you cannot see that because all of them are overlapping with the exact solution. Okay? So this is perfectly nice. However, so this exact one is Gaussian, exponential of minus x squared, but the neural network doesn't have that function. So it consists of activation function and linear manipulation. So in fact, if you look at inside of the wave function, then it looks like this. The ground-state wave function is some number times soft plus, and input of soft plus of is a of x, which is written like this. It's a linear combination of 4 a functions. All of those are soft plus. Okay? So this is not Gaussian. However, if you plot this, then it perfectly matches. So I'll come to the interpretation of this one later. That is important for discrete geometry. All right, so what about two particles? One-dimensional harmonic oscillator. So x and y correspond to the first, so location of the first particle and the second particle. So it's effectively two-dimensional, one particle. And you can also introduce some interaction between these two particles, like this one. It could be anything. The neural network is like this. So wave function needs to be two-dimensional. So 1 unit output, but 2 units input. So depending on whether these particles are bosons or fermions, in fact, this final function needs to be symmetrized or anti-symmetrized. So it is possible to implement this symmetrization procedure inside of this neural network, but it's very complicated. So what we do is that, okay, we have the ordinary neural network, and then I go outside, and then I symmetrize this, and then substitute that to the Hamiltonian expectation. Okay. So symmetrization comes after that. So this simplifies the procedure a lot, and in fact, it worked very well. So this is a result. For exact solution at interaction equal to 0, you have these exact solutions. For bosons, you have energy equal to omega, fermions, energy is equal to 2 omega. And in fact, in your left-hand side, we have this numerical result. And if you look at lambda equal to 0 part, the no interaction, then energy is equal to exactly equal to distance. So it's great. And if you turn on this interaction, then energy deviates from this no energy. Then you can also plot the wave function. For example, for the boson case, this is the no interaction exact solution. So all of them are Gaussian. And if you look at the neural network result, which is on the right-hand side, for example, this one with no interaction should match with this exact one. And yeah, they match. And if you include, for example, some repulsion interaction like this, lambda positive, then these two separate makes separate. So it's physically correct. And also for fermions, you can do the same, and you have this result. So they look, again, they look perfectly match each other, and interaction property is physically sensible. So this is the end of this quantum mechanical solution using neural network. And then I'd like to use this story to find discrete geometry, which is our purpose. Yeah, please.
If you don't do the harmonic oscillator, you do x to the 4 or x to the n, the results just interesting.
Sorry, what do you mean x to the 4?
I already knew what the harmonic oscillator rate was. You did x to the 6 to
yeah, of course you can do that. Yeah.
Does it give answers that are just that?
So I would say that the potential shape doesn't matter if it is bound from it, then this works perfectly nice. So the demonstration here is only for comparing with the exact solution in known cases. And yeah, so they match quite nicely. So I mean that if you have your favorite Hamiltonians, you can do this one and then, yeah.
If you go to higher dimensions, atomic physics,
yeah, so that's the important question. So if I go to higher dimensions or multi-particles, then I need to wait more, since the number of parameters diverging exponentially. So the training needs a lot of numerical power. So I think for this kind of simulation to work with my laptop, then at the most, I think I can have only 3 or 4 particles.
in higher dimensions.
In 2 dimensions, for example. If you go to 3 dimensions, then, well, for example, I'd like to do a spectral analysis of atomic nucleus, for example, then helium is quite difficult still. Yes, Ben?
Just because the case adds some more sophistication on the architecture and incorporate more services effectively, then this should scale up as well. Because when you're looking at things like the neural networks, to just predict trajectories of particles, this scaling was achieved by using graph.
I see.
In that sense, I would imagine that.
Yeah. I see. Thank you. So since I have used a very naive neural network, if I have a more sophisticated architecture, then the number of parameters can be reduced quite much. And yeah, so we better discuss that later. Yes, sure. So here, for this demonstration, as I showed you, for example, in this harmonic oscillator case, you can see that the total energy becomes 1/2, even though, even with this very simple neural network. You have a single layer, just 4 units, it can reproduce Gaussian perfectly. So this means that there is some hint for reducing the number of parameters efficiently, or I mean, question-wise, but so let's discuss this.
Sorry to be going on.
Yeah.
Usually the variation like that, which you will roll low. But you can't really look through the true grasp.
Well,
so it means you've got a wave function that has precisely that.
So I would say that since this is so this also yeah. So I'll come to that question in later sections. But here, since we have this soft plus activation function rather than some other activation function, this may help reducing the error from the exact solution. Since we know that the exact solution is Gaussian, right? It's made by smooth function interpreted like this.
The question is slightly different. So any variation, any ansatz for a wave function must have an energy that's bigger than the true ground state.
Oh, you mean big numbers that
That's relation.
Yes, yes. So these numbers are below 0.5. Yes. So this small deviation is due to the numerical error. Yes. Thanks. Okay, so let me go to the next section about the discrete geometries. So this is a Gaussian function which neural network found, but it's not Gaussian, but it looks, so if you plot it, then it looks like a Gaussian. So to find an interpretation of this neural network training function, I just replace this soft plus by ReLU. Okay? Soft plus is a smooth function. I replace that by ReLU, which is a kinky function. Then it looks like this. So this blue dashed line, which goes from here like this, So this is the function given by this, but soft plus is replaced by ReLU. So as you can see, I'm sorry, 0 is here, but in this picture, 0 is here. Okay. So it starts from 0, and then it has a triangular shape, and it goes back to 0. The interpretation is obvious, right? Here you have kick, you have kink here. And these kink are produced by activation function, since ReLU is producing the kink. And if you look at this A of ground state, so this function, rather than psi of ground state, then this is before having this soft plus to get the ground state wave function. So what is this function? If you plot this by replacing soft plus by ReLU, then you have this purple dashed line. Okay. So you have this triangle, then acting ReLU here, it cut off the part below 0. Then you have this shape. So this is how neural network approximates the things. So it's a piecewise approximation. You have this part, this part, this part, this part, and these are chosen so that it approximates this Gaussian function. So you can do this game for 2 dimensions. For example, this is a 2-dimensional Gaussian. And I train this with the neural network. And let's replace soft plus by ReLU. Then you get this thing. So this is a piecewise linear function, which has this mountain, and the shape is kinky. And there is a nice parametric connection between ReLU and soft plus. You can introduce one parameter and then go continuously from soft plus to ReLU. And if I make a movie, then it looks like this. Okay, finally, it evolves to some kinky things. Like this. So this means that smooth surface can be approximated by kinky surface, and that has finite number of parameters. So this is what I want for quantum gravity. So quantum gravity is for smooth surfaces, and I want to approximate it by a function which has a finite number of parameters. It was possible by neural network. For example, I can use this technology to approximate a smooth surface by discrete geometry. So this is called sharp surface, whose height is given by this function. So x and y is here, and the height is given by this function. This function is a minimal surface whose boundary is given by this bed-shaped boundary condition. Then this is a smooth surface. Minimal surface is given by this configuration. And I try to approximate this function by neural network. So input is 2 dimensions, x and y. The output is height function. If I use, for example, the neural network architecture with 4, 4, 4 internal neurons for each layer, I specify by this kind of numbers, then the result looks like this. If I increase the number of units for intermediate layers, then I have this. If it is 20, then it's completely smooth to our eyes. And for example, if you look at this thing from above, it looks like this. And we are familiar in ADS-CFT community, this is familiar, this is ADS space, the hyperbolic space. So hyperbolic space is automatically partitioned into discrete patches. And it reproduces, it's an approximation of the original surface. So here the point is that I didn't specify the way to partition the space. It's automatic. Once your architecture is specified, then this discretized geometry is generated automatically.
What measure is close to our?
Oh, I see. Thank you for the question. The measure for approximating this function is just the height difference.
Why?
It's I didn't say that it's a good measure. So there it's one measure.
Is there a way to assess?
Sure. So for example, suppose that you don't know the resultant function for this surface, right? So suppose you have only the bound, so you know only the boundary condition, and you want to minimize the surface area. Okay. So even in that case, you can use neural network, resultant neural network function. From that function, you compute the area, and then you try to minimize it. So in this way, you can choose your own loss function as your favorite one, and then try to do this kind of program. Did I answer your question? Yeah, so I didn't say that this is the best way to approximate the solution, and it's up to you what kind of loss function you try to use. So it could be Einstein action, for example. All right. So you would say that, yeah, so this is a smooth surface. But in reality, in quantum gravity, you have many spiky surfaces, which could contribute to the geometry. And yes, so let's try this kind of thing. So upper series, you have this target geometry, which I artificially put some spike here. This has 4 spikes. And then I use the same neural network architecture to approximate this. Then it automatically produces this pyramid here. I didn't do anything. I just run the program with this architecture, then it automatically produces this thing. Even though you have many spikes, it produces these spikes nicely. So there is no fine tuning of what kind of mesh you need to prepare for this. It's automatic. And this automaticity is quite important for discrete geometry community. Since, for example, in polygons, in C computer graphics, what you have to do is to discretize your body surface into lattices, but you need to specify the points and how those points are connected. But here, if you use your network, then you don't need to do that. You have a space, so points, so the set of points which specify the target target geometry, and then source that into some neural network, then it discretizes automatically. So this sounds quite nice for discrete geometry. And so what is the benefit I summarize? So first, it's a computation easy way to get discrete geometry. So you don't need to specify the points and lattice and mesh. And it works even when no smooth surface is given. For example, if you want to solve the minimal surface problem, then first, maybe you thought that you need a surface function, but you don't need it, since this is minimized automatically. And then thirdly, as I said, you can replace this soft class by ReLU, so you can interpret smooth and discrete. Quite nice. So how can we use these benefits for quantum gravity? So first, there is so-called Nash embedding theorem saying that any space can be embedded as a surface in higher dimensions. So if you consider some geometry which is called space-time, then you can embed that in higher dimensions. Then you can think of it as a surface program. Okay? So this is good for quantum gravity. And second, as I said, loss function can be chosen as your favorite one. So I can choose Einstein-Hilbert action as a loss function in Euclidean case. Then I minimize it. Then it solves the Einstein equation. And third, what is the path integral for quantum gravity? Since this geometry is given by neural network and it has a finite number of parameters. So if I can make an integration over possible weights, then it is automatically generating possible geometries, which are discrete. So I would say that this is a quantization in space. And this is numerically done. So, but you remember the history of quantum gravity. It was very hard. And in fact, in 1990s, the quantum gravity path integral was possible only for 2 dimensions. So why? Since even though you can define path integral in this way, the point is that whether you can find a critical point by using some scaling is important for having a continuum quantum gravity. So here I don't make sure that we can find this second order critical point by using our technique, but this is a kind of first testing ground for having a summation of a discrete geometry. Sure. So thank you for the question. So this loss function can be anything I said, but of course it needs to be bounded so that I think it can be minimized. So in the Lorentzian case, I don't know what I should do, but at least for Euclidean case, I think we can do. In what?
Wrong side. There's some bounded decisions in Euclidean about that. The formal fact is the actions.
I see. So yeah. So it's how we define the quantum gravity, right? So if you want to make the path integral to be consistent, so naive Einstein-Hilbert action doesn't work, right? It's what you see. So this means that, for example, in physics informed neural network, what we do is, if we want to solve a partial differential equation, then we have a square root of it. Then we minimize that. Then that solves the equation, right? So in this way, you need to prepare some bounded function as a loss function. So if I use Einstein equation, the Einstein equation squared would be the candidate for the loss function. But I don't know whether it leads to quantum gravity or not, since the deviation from the Einstein equation is specified in this loss function. So yeah, let me discuss that later. That's an interesting part. Yeah, please. So this is again the definition of what kind of measure when for you to do a quantum gravity. So this is you can include this arbitrary kinds of weight function for the measure of the weights integration, and that defines your quantum gravity definition. So here normally what we think of about quantum gravity is that the measure needs to be diffeomorphism invariant. And here, since the meaning of weight is quite complicated, so I think it's not easy to find such a nice measure in this program. So this is a kind of fatal part of that. Yeah, please. So when I talked about this number 3, then it's already quantum, right? So it's wave function itself was. Yeah. Yeah. That's right. Yeah, I agree with you. Yeah, I have to think of that. Thank you. So how many minutes do I have? It's several, 5 minutes. Thank you. Yes. So I come to the final section, neural polytopes. Here I try to approximate sphere by using this technique by discrete geometry. Okay. So as I told you in the first section, our goal is to find geometry generated by neural network. And let's compare this with the quantum gravity history. So there are Regge calculus and also dynamical triangulation. And this was successful, but it also has some problems. So we might try this kind of thing to generate discrete geometry by using very different technique and see whether it goes to some hint about quantum gravity. So for this purpose, first I need to try a very simple, the simplest geometry, whether it can be approximated by neural network or not, and that's a sphere. So I prepare this kind of neural network where, for example, if you want to find a d-1 dimensional sphere in d-dimensional space, then the input is just d-dimensional coordinates and output is this function. And this neural network, for example, you can have a ReLU activation function. I use a generalized ReLU, which looks like this, rather than this. Yes. The reason, and P is a variable number, and it is fixed to be, for example, 1 for fun training, but you can change it. And this neural network has no bias. So I may explain that, but maybe I don't have time for that. So anyway, we prepare this neural network, and the target supervised training data is just 1, since in the radial coordinate, the radius equal to 1 in the sphere. And I try to approximate this sphere by a piecewise linear function. And here is the result. In one-dimensional case, to approximate a circle, you have these results. And these results for different architecture. So for example, for this, I have 2 units in the hidden layer. For this, I have 3 units, 4 units, and I vary the number of units. Then I have different, very nice shape of polygons. And then for S2, in the same way, I can change the number of neurons like this. So I can vary the architecture. Then I got these things. So these are regular polygons, quite nicely reproduced. And you can find semi-regular polygons like this. You see the nature actually do the same thing. Like this. And you can do for higher dimensions, like this. And also, as I said, the activation function was chosen to be x to the power of p, where p is equal to 1. And the result was shown here, and here, sorry, here, and here. But I can change this p deviating from 1.0, like this. So if it is going smaller value, then it goes more spiky like this. If p is more than 1.0, then it goes to a round shape and then goes to this way. The reason why you have a perfect sphere here and here for p is equal to 2 is that the defining function for sphere is x to the squared plus y to the squared plus z to the squared. So the power 2.0 is for the definition of the sphere. And if you go over that, then it goes back to polygons. And in fact, if you look at that P is infinite and P is 1, then these are dual polytopes. The dual polytopes means that you pick a center point of these faces, then you get this one. And then you have a center point of these faces, and you get this one. So this is the duality of polygons. And those are reproduced by these neural networks. And in fact, this can be easily seen by the change of the activation function. For P for 1, it is this, but for P for infinite, it is this. So these actually serves as a duality of polytopes. So in this way, it was, so this discrete approximation of sphere is kind of nicely done by neural network. So as a summary, I prepared this neural polytopes for the approximation of spheres, and this could be used for a summation over different geometries using machine learning. Okay, thank you very much.
Before we start discuss this continuous quantum mechanics, you showed us how one can use neural networks to approximate wave functions of spin chains, right? So, and you mentioned, I guess, Heisenberg spin chain, it is integrable spin chain. And my question, but in principle, you can of course try to solve any. So, in my question, did someone try to see the difference on level of the structure of this wave functions as neural networks to distinguish between integrable and non-integrable? Is it visible, or from neural networks it looks all the same more or less?
Thanks. That's an interesting question. I have no good answer to your question, since it's supposed that neural network actually works for many kinds of spin systems. So,
of course, yeah.
For integrable systems, since you have the answer to the energy, for example, energy eigenvalue distributions, so you can actually compare the result with those integrably solved.
Yeah, of course. My question, level of structure of wave functions. Did someone take a look into it?
That part I don't know. Since
Okay.
one thing I can tell you is that although using neural network can actually lower the energy eigenvalues, but the result, so interpretation of this result and obtaining neural network is quite difficult.
Yeah.
So since so if you start with, for example, the fully connected neural network, then it's completely non-local. So what kind of good correlation among spins are working is the question.
Okay. And as a continuation of that discussion on path integral, maybe the ultra simplest case will be again spin chains, because it is finite dimensional Gilbert space. So maybe you can try to perform your integrals over weights, maybe.
Yeah.
By the way, do you know what this taking ReLU instead of something smooth will mean for spin chains type?
Do we have further questions? Well, if not, then let's thank the speaker again.